Exponent Rules Part 5. This is about exponential functions. Now, in this part, all I want you to do is watch the examples, okay? We'll take our formal notes when we're back together in class on Wednesday. Just watch here. I just want to do a few examples for you so you kind of get an idea of where we're headed, all right? So no need to take any notes, just kind of watch and follow along. How do we graph these things? Remember that f of x is the same as y equals a times b to the x. So first time we're looking at a function here that's not a linear function. Notice the exponent here is where the x is. So a and b will be numbers. Let me make up a quick exponential function. So let's say f of x equals 3 times 2 to the x power. X, y. We need to try a bunch of different numbers here and see what happens. Let's try 0, 1, 2, 3, and let's look at what an exponential function looks like. Well, I want to follow my order of operations. F of 0, remember that notation means 3 times 2 to the 0 power. So let's think back on our exponent rules and our order of operations. Order of operations says do the exponent first. 2 to the 0 power is 1. 1 times 3 is 3, so f of 0 is 3. F of 1 would be 3 times 2 to the first power. Exponents first, 2 to the first is 2, times 3 is 6. F of 2 would be 3 times 2 to the second power. 2 to the second is 4, times 3 is 12. And we notice, as we build these up, we're not increasing at a constant rate, right? It's not plus 3, plus 3, plus 3. We have all kinds of different numbers in there. Let's do one more. F of 3 would be 3 times 2 to the third. 2 to the third is 8, times 3 is 24. In fact, what happened each time out here is we doubled each time we expanded our x. So let's see what those points look like. When x is 0, y is 3. When x is 1, y is 6. My neighbor is doing yard work, sorry. When x is 2, y is 12. When x is 3, y is 24, so it would be way up off the graph. So there's a different number between each value. I wonder what would happen if we went backwards instead. So if we continued this idea and did x is -1, -2, -3, let's see what would happen. So I'm going to ignore this g of x for now. And let's find f of -1. So that would be 3 times 2 to the -1. So what does that negative exponent mean? Let's see, it reciprocates that base. So it would make it 3 times 1 over 2, 3 times 1/2, which would be 3 times 1/2 is 1.5. F of -2 would be 3 times 2 to the -2. 2 to the -2 is 1 over 2 squared, or 1/4. 3 times 1/4 is 3/4, or 0.75. Notice again, there's no negatives there, right? I'm not including a negative in the base. It's just that the exponent is reciprocating that value. F of -3 would be 3 times 1 over 2 to the third, which is 3/8, which I think is 0.375. Somebody can check my math there. Let's see what happens when we go backwards. F of -1 is 1.5. F of -2 is 0.75. F of -3, 0.375. So this is what an exponential function looks like. It curves nicely. It starts growing slowly, and then it continues to grow faster and faster by the same amount. Between each time we jump up an x value here, we're doubling. It's doubling because I made the base 2. If that base was something else, we'd be bouncing up by a factor of that number. Think about what would happen as x got smaller and smaller and smaller and smaller. Will that value ever equal 0? Well, the answer is no. This is one of my favorite ideas in math. It's going to approach that x-axis, but it's never going to touch it. It's going to get closer and closer and closer. If x was negative 1,000, you would have 3 times 1 over 2 to the 1,000th power, which is a huge number. But when I divide by it, it just gets really, really tiny, times 3. It's never going to be negative. That line that a function approaches but never touches, one of my favorite math words, that's called an asymptote. Isn't that a cool idea? A line that a curve approaches but never touches. It gets really, 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 really close, infinitely close, never touches. That's very cool. So exponential functions, they look like this. Couple things to notice. First of all, the y-intercept of this function was 3, right? That y-intercept comes from this number. That number that's in front of the parentheses, that's not part of the base, that will always be your y-intercept. And it comes because when x is 0, this part will be 1. 1 times that value is our y-intercept. Let's take 2 more quick looks. Let's say, what if I reversed those values from the last one? What if I made my f of x 2 times 3 to the x instead of 3 times 2 to the x. So y equals 2 times 3 to the x. We're going to do the same thing here. We'll do x and y. I'll go negative 3, negative 2, negative 1, 0, 1, 2, 3. So we'll figure out all of these values for y. I'm going to start with the higher values because it's a little easier to do that arithmetic. So if x is 3, so I'm going to start down here. If x is 3, y would be 2 times 3 to the third power. 3 to the third is 3 times 3 times 3, 27 times 2, y would be 54. If x was 2, we'd have 2 times 3 to the second. 3 times 3 is 9, times 2 is 18. If x is 1, that would be 2 times 3 to the first power. 3 to the first is 3 times 2 is 6. If x is 0, that's 2 times 3 to the 0 power. Again, 3 to the 0 is 1, times 2 is 2. Now I want to pause for a second and let's look at the pattern here and see what's happening. Every time the x increases by 1, again, we don't have a constant rate of change. It's not increasing by the same amount, but it is increasing by the same factor. We're multiplying by 3 each time we jump up 1 in the x direction. And again, that's because that base is 3. Let me continue to go backwards. If in this direction we're multiplying by 3, we would expect that in the other direction we're probably dividing by 3. So let's see what happens when x is negative 1. That would be 2 times 3 to the negative 1. 3 to the negative 1, again, is the reciprocal of 3. 2 times 1/3 is 2/3. So again, it took that 2 and it divided it by 3. If x is negative 2, 2 times 3 to the negative 2. 3 to the negative 2 is 1/9, times 2 is 2/9. So again, it's just cutting by a factor of 3, or dividing by 3 each time out. And I would expect to the negative 3 would be 2 over 27. Now again, we notice never hit the negatives, right? It's just getting smaller and smaller and smaller, these positive values, as x gets more negative. So if I wanted to graph those, let's see, 3, 54, I couldn't fit on the graph, it's way too high up. 218 would be here. 16 would be here. 02 would be here. And what I said in the last slide was that y-intercept comes from that initial value, that coefficient of our exponent. If x is negative 1, y would be 2/3, right about there. If x is negative 2, 2/9, 227. So it's getting smaller and smaller and smaller. We have that asymptote. Again, then there's an exponential function. So I'm going to do one more. When the base is less than 1, what happens if we have a fractional base? All right, so let's say we're looking at f of x, or y equals 4 times 1/2 to the x power. So again, I've got my x and y, and I'll plug in a bunch of different numbers. Again, I'll go negative 3, negative 2, negative 1, 0, 1, 2, and 3 to see what happens, what this function looks like evaluated at each of those numbers. And again, I'm going to start at 0, and I'll work my way up this time. And again, the same idea. If x is 0, 4 times 1/2 to the 0 power. 1/2 to the 0 is 1 times 4 is 4. If x is 1, then I have 4 times 1/2 to the first power. 1/2 to the first is 1/2. Half of 4 is 2. So what happened in that jump between 0 and 1? That function decreased. Well, what if x is 2? If x is 2, we have 4 times 1/2 to the second power. 1/2 to the second is 1/2 times 1/2, which is 1/4. 1/4 of 4 is 1. So what's the pattern here? What's happening each time our x changes? If x is 3, that's 4 times 1/2 to the third, which is 1/8. 1/8 of 4, that's 1/2. So again, that continued pattern, right? Everything is getting cut in half as the x gets bigger. So what would happen if the x went the other direction? What if x was -1? 4 times 1/2 to the -1. Well, we said in our notes last week, when we have a fraction to the negative first power, it flips that fraction over. That's the same as 4 times 2 to the +1. Well, that's 8. So now look what's happening. Now as the exponent gets smaller, the base is actually causing the function to double. 4 times 1/2 squared, or to the -2, sorry, would be 4 times 2 to the +2, which is 4 times 4, which is 16. And again, it doubled, and we would expect the next one to be 32 because it's doubling. So let's look what this function looks like. If x is -3, y is 32. That's way, way up there, won't fit on the graph. If x is -2, y is 16. If x is -1, y is 8. If x is 0, y is 4. And just pointing out again, there's that y-intercept at that coefficient. Let's see, when x is 1, y is 2. When x is 2, y is 1. When x is 3, y is 1/2. This function decreases. So what we're going to talk about in class on Wednesday is kind of notation and some formalized notes for these functions. So you've seen a few examples. We'll get the formalized notes on Wednesday. See you all tomorrow, guys. Take care. Bye-bye.